What if everything we thought we knew about the moon was based on only half the story? For thousands of years, humans have stared up at the same familiar face, drawing myths, writing poems, and building science around it, never once seeing what was hiding on the other side. And now, for the first time ever, something has been brought back from that hidden half, and what scientists found is quietly rewriting the history of our closest neighbor. Before we go deeper into this incredible story, do me one small favor. If you love space, mystery, and the kind of discoveries that make you rethink reality, hit that like button, smash subscribe, and share this video with someone who still believes the moon is just a boring gray rock. Your support is what keeps stories like this alive on this channel. Now think about this for a moment. In the entire history of humanity, we have brought back just under 383 kilograms of moon material. That includes 6 Apollo missions from the United States, 3 Soviet robotic missions, and China's own Chang'e, 11 successful sample returns spread across more than 50 years of effort. And here's the strange part. Every single one of those samples came from the same side of the moon, the near side, the face we always see. Every rock studied in every lab on Earth, every textbook diagram, every model of how the moon was born and how it slowly went silent, all of it built from material scooped up on just one hemisphere of a world that has 2 very different faces. And when I say different, I don't mean slightly different. I mean shockingly different. Look up at a full moon tonight and you will notice those big dark patches. Those are ancient lava plains, frozen oceans of molten rock that once flooded the surface billions of years ago and then hardened into stone. They give the moon that classic face in the sky look that every culture on Earth has interpreted in its own way. But turn the moon around, look at the far side, the side we never see from Earth, and those dark seas almost completely vanish. The far side is pale, it is heavily cratered, its crust is thicker, its chemistry is different, its volcanic history is different. It is like looking at a twin who grew up in a completely different world. Scientists call this puzzle the lunar dichotomy, and for decades no one could explain it. There were theories, of course. Maybe the huge magma ocean that once covered the young moon cooled unevenly, hardening faster on one side than the other. Maybe the pull of Earth's gravity heated one hemisphere more than the other. Maybe a giant impact reshaped everything early on. All reasonable ideas. But without actual rocks from the far side, every theory was just a guess wearing a lab coat. You cannot solve a mystery about stone without holding the stone in your hand. And that is exactly why one specific landing site on the far side became the most important patch of dirt in the solar system. On the far side, in the southern hemisphere, there is a wound so massive that it seems almost unreal. It is called the South Pole Aitken Basin, and it is the biggest confirmed impact scar anywhere in our entire solar system. Roughly 2,500 kilometers across. The deepest structure on the moon, and also the oldest, formed somewhere between 4.2 and 4.3 billion years ago, back when the solar system itself was young, chaotic, and constantly being pounded by giant chunks of rock. Whatever hit the moon to carve that basin didn't just leave a dent. Gravity readings show that the moon's crust beneath parts of it is among the thinnest anywhere on the entire lunar surface. Computer models suggest the impact tore out material from as deep as 80 to 120 kilometers below the surface, reaching down through the lower crust and quite possibly straight into the mantle itself. Now inside that giant scar sits a smaller one called the Apollo Basin, about 490 kilometers wide. And inside that, on a flat, dark plain of ancient lava, is where China's Chang'e 6 mission touched down. The coordinates were around 41 degrees south and 154 degrees west. The ground around the landing site was scattered with ridges and small islands of older rock that the ancient lava flowed around rather than covering. The lander itself settled right on the edge of a small crater about 50 meters wide and 3 meters deep. The basalt underneath was ancient, dated to somewhere between 279 and 2.87 billion years old. The hope was very simple, but also incredibly bold. If the original impact really did punch that deep, then bits of the moon's inner mantle might still be lying scattered on the surface. Scoop up the soil here, and by pure luck, you might be scooping up the inside of the moon itself. Chang'e 6 lifted off on the 3rd of May 2024 at 9:27 in the morning Universal Time, riding a Long March 5 rocket from the Wenchang launch site on Hainan Island. It was the 6th robotic moon mission from the China National Space Administration, and like everyone before it, it was named after the goddess of the moon in Chinese mythology. The full spacecraft weighed about 8,200 kilograms. The lander alone weighed 3,200. The tiny ascent vehicle that would eventually rocket the samples back off the surface weighed about 700. 5 days later, it slipped smoothly into a 12-hour orbit around the moon. But here is where the mission ran into a fundamental problem, one that no near-side mission has ever had to deal with. You cannot talk to a spacecraft on the far side of the moon. Radio signals cannot bend around 3,170 kilometers of solid rock. Every single command, every piece of telemetry, every fragment of data had to be routed through a middleman. That middleman was a satellite called Queqiao-2, already parked in a very specific orbit where it could see both the far side of the moon and the Earth at the same time. Without that relay satellite, Chang'e 6 would have been completely deaf and mute the moment it crossed the horizon into radio silence. On the 30th of May, the lander and ascender separated from the orbiter. 2 days later, from an altitude of 200 kilometers, the descent began. And this is where things get really impressive. The spacecraft had to come down completely on its own using an autonomous obstacle avoidance system. A visible light camera scanned the ground. A laser three-dimensional scanner mapped the surface in real time. The onboard computer picked out boulders, spotted dangerous slopes, and steered around them without a single human being in the loop. There was no time for humans to intervene. There was no signal path for humans to intervene through. 17 minutes after it began its descent, the lander was safely down on the far side of the moon. Then the real work began. A robotic scoop went to work on the surface soil. A separate drill reached about 2 meters below the surface. The scooping was done in 8 careful passes at one location, each one going no more than 3 centimeters deep, gathering roughly 1,610 grams of loose material on its own. And here is a beautiful little detail. When the drill was pulled out, the hole it left behind in the lunar soil happened to form the shape of a Chinese character, Zhong, the first character in the Chinese word for China. Nobody planned that. Nobody could have. But within days, images of it were spreading across Chinese social media like wildfire. There was also another small passenger on this mission. A mini rover weighing just 5 kilograms, wrapped in shiny gold insulation that earned it the nickname Jinshin, meaning golden toad. It carried its own tiny solar panels and an infrared spectrometer to study the soil composition and search for water ice. But it also had a much simpler and almost artistic job. After the sampling was done, the little rover drove away from the lander, picked its own angle, and took a photo of the lander sitting alone on the far side of the moon. It composed the shot on its own. No human directed it. No signal from Earth guided the camera. At 10:38 at night on the 3rd of June, the ascent vehicle fired its engine and lifted off the top of the lander. And that moment is worth pausing on. It was the very first time in history that anything had ever launched from the far side of the moon carrying a cargo. 3 days later, at 6:48 in the morning, the ascender found the orbiter waiting in lunar orbit and docked with it automatically. 2 robotic spacecraft finding each other above the moon with no pilot on either side. 36 minutes after that, the sample container was transferred to the return capsule. And then the mission went quiet. On the 21st of June, the service module appears to have fired its engines to leave lunar orbit. There was no big announcement at the time. What we know comes from scattered reports by amateur astronomers and radio observers around the world who spotted something that looked very much like an engine burn. 4 days later, a re-entry module weighing about 300 kilograms separated from the service module and slammed into the top of Earth's atmosphere over the Atlantic Ocean. But it didn't just fall straight down, it skipped, actually bouncing off the atmosphere once to shed some of its terrifying speed, the way a stone skips across water before committing to its final descent. At 6:07 in the morning on the 25th of June, a parachute opened over Siziwang Banner in Inner Mongolia. Helicopters were on scene within minutes. 53 days from launch to recovery, and now the real detective work could begin. Take a breath here, because what comes next is where the story stops being about engineering and starts becoming something genuinely strange. But before we get into that, if this story is pulling you, drop a comment below with the word moon, so I know you're still with me. Every comment tells the algorithm this story matters, and it helps me keep bringing you deep dives like this one. And if you haven't yet, tap that subscribe button, because trust me, you do not want to miss what comes next. 3 days after the samples arrived, there was a ceremony in Beijing. Zhang Kejian, the head of the Space Administration, formally handed the sealed container over to Ding Chibiao, vice president of the Chinese Academy of Sciences. Certificates were signed, photos were taken, and then Gay Ping, the mission spokesperson, said something at the press conference that most people just glossed over. He said the samples were more viscous than previous samples. He said there were clumps. He was very careful with his words. He called these observable characteristics, not conclusions. A man simply describing what he could see with his own eyes, refusing to say what any of it actually meant. But looking back now, he was describing the very first discovery. It just did not look like a discovery yet. The very first measurement anyone took was density, and the number came back wrong. Not a little wrong, meaningfully wrong. Lunar soil from the near side sits in a fairly well-understood range. The soil from Chang'e 5 had a bulk density of about 1.24 grams per cubic centimeter. The Apollo samples range from about 0.75 up to 2.29. But the Chang'e 6 soil measured just 0.983 grams per cubic centimeter. That is barely denser than water. Let that sink in for a moment. The very first material ever brought back from the far side of the moon was fluffier, lighter, and less dense than any lunar soil we had ever handled before. Not slightly, measurably, consistently, both in the bulk density and in the true density of individual grains. And remember, this was measured on Earth under Earth's gravity, after being shaken through a violent launch, a fiery re-entry, and a bumpy landing. On the actual surface of the moon, in its natural state, it would have been even looser, even fluffier, almost like frozen powder. So the obvious question, the one every scientist immediately asked, was why? Why is the soil so light? The answer turns out to be about ingredients. Lower density means lighter minerals inside. And when researchers ran the mineral analysis, the ingredient list looked nothing like the near side. The soil was made up of about 32.5% plagioclase, a pale, low-density feldspar, almost 20% augite, about 10% pigeonite, around 3.5% orthopyroxene, just under 30% amorphous glass. And olivine, which is a dense, heavy mineral, showed up at only half of 1%. To put that in perspective, the Chang'e 5 soil from the near side had about 4.3% olivine and about 20.7% glass. The far side sample had roughly 1/10 of the olivine and quite a bit more glass. It was a completely different recipe. But the tiny detail that mattered most was the orthopyroxene. That specific mineral is not typical of the local basalt at the Chang'e 6 landing site. Its presence means something. Arrived there from somewhere else, and that leads to the second big finding. This soil is not local. Based on the proportion of orthopyroxene inside the total pyroxene content, researchers estimated that at least 11% of the sample was foreign material, debris thrown in from other places on the moon. Factor in the extra plagioclase, and that fraction could be even higher. Analysis of the bright ejector rays crossing the dark plane around the landing site independently suggested contamination of at least 13%. In simple words, the container held a mixture of local ground plus wreckage flung in from other impacts, some of them possibly reaching very deep into the moon indeed. The grains themselves were almost unimaginably fine. Researchers counted more than 72 million individual particles smaller than 1 millimeter. About 95% of them fell between roughly 1 and 11 micrometers across, averaging about 5.5. In geology terms, that is clay to fine silt. In practical terms, it is dust. It is the product of billions of years of tiny meteorites relentlessly bombarding the surface, slowly grinding solid rock into powder inside a perfect vacuum. Nothing on Earth grinds like that, because nothing on Earth is exposed like the moon. Among that dust sat larger fragments too. Basalt made up about 30 to 40% of them. Breccias, which are broken rocks welded back together by ancient impacts, made up another 30 to 40%. Agglutinates, which are grains of soil fused together by impact glass, made up 20 to 30. And about 10% were pale fragments dominated by anorthosite and norite. There were even glass beads, small rounded droplets colored black, brownish yellow, white, and green, each one a frozen memory of some ancient collision. Chemically, the local basalt was low in titanium, low in aluminum, and low in potassium. The soil showed very little uranium and very little thorium, far below the levels found in the potassium-rich areas that dominate the near side. Whatever this place was, it had not been built from the same material that produced the great dark seas we can see from Earth. This was a different kind of moon, so now the researchers had what they call ground truth. They knew what the far side was actually made of. But that only raised a bigger question. What had actually happened here? What event, what force, what ancient day had shaped this place into something so different from the world facing us? That question landed on the desk of a research team at the Institute of Geology and Geophysics of the Chinese Academy of Sciences, led by Professor Tian Hengqi. And what they figured out began with an insight about a single element, potassium. It sounds boring. It isn't. Potassium is what geochemists call a moderately volatile element. That means it doesn't need to be blown apart to leave a rock. It just needs to get hot enough, and then it simply evaporates. And when potassium evaporates, it doesn't leave in equal amounts. Potassium comes in more than one form. Potassium-39 is lighter. Potassium-41 is heavier. When molten rock boils away into a vacuum, the lighter version escapes faster and easier than the heavier one. What is left behind becomes gradually enriched in the heavier version, which means the potassium locked inside a rock is basically a thermometer. Not a thermometer of today, a thermometer of the worst day that rock ever had. If you can measure that ratio precisely enough, you're literally reading a record of temperature, pressure, and history left behind by an event that happened billions of years before there was anything alive on Earth to see it. And this is where the team hit a serious wall. The Chang'e 6 samples were mostly dust. Finding individual grains large enough to work with was incredibly hard. And precision potassium measurement had always required much more material than they had. Professor Tian later described this as the biggest technical challenge of the entire study. Not the physics, not the modeling, not the interpretation. Just having enough rock. So instead of asking for more samples, they did something remarkable. They rebuilt the method itself. The team developed an ultra-low consumption potassium isotope protocol, capable of high precision measurement at the milligram level. In the end, they worked with 4 small basalt fragments. The heaviest weighed about 19 milligrams, the lightest just 14. 4 tiny stones, hand-picked out of the soil under a binocular microscope inside a clean laboratory, washed carefully in ethanol to strip away any clinging dust, and then scanned by X-ray tomography to confirm what was inside. Them without cutting them open. Then they were dissolved, purified, and finally fed into a mass spectrometer. And the result did not match anything from the near side. The Chang'e 6 basalts were isotopically heavier in potassium than every previously documented lunar sample. Heavier than Apollo, heavier than Chang'e 5, heavier than the lunar meteorites that occasionally fall on Earth. The offset averaged about 0.16 parts per thousand above the Apollo baseline. The iron isotopes came out heavier too. Now, in the world of isotope geochemistry, differences that small are never taken lightly. They are attacked from every direction. So the team went hunting for every boring explanation they could imagine before they even considered anything more dramatic. Could it be cosmic rays? Over hundreds of millions of years, radiation constantly hitting the lunar surface can slightly alter isotope ratios through nuclear reactions. The team calculated the maximum possible contribution, even assuming an exposure age of 1 billion years, which is the upper limit for most lunar samples. The effect landed comfortably inside their own margin of error. Not enough. Could it be contamination from the surrounding fine soil? Fine lunar dust does sometimes carry heavy isotope signatures from long exposure to space weathering, but their 4 fragments had been ultrasonically cleaned, and the X-ray scans showed no impact, breccia or melt glass inside them. Clean rock? Could it just be ordinary magma chemistry? Here, the answer split in 2. Modeling of partial melting and fractional crystallization could largely explain the heavier iron, but potassium behaved differently. Because of how potassium moves during melting and crystallization, those processes leave its isotope ratio essentially untouched. The magma itself simply could not have created the signature. Could the impacting object itself have mixed into the mantle and changed the numbers? The team ran calculations for chondrite-type meteorites, for iron meteorites, and for large Vesta-like bodies. Chondrites would have made the isotopes lighter, not heavier, and would have left a nickel fingerprint that just isn't there. Iron meteorites contain almost no potassium at all, and a Vesta-like impactor would have needed at least 7% of its residue to survive inside the lunar mantle, while also shifting the iron isotopes in the wrong direction. Impossible. One by one, the ordinary answers failed, which left only the extraordinary one. Here is what the data quietly suggested. The mantle beneath the South Pole Aitken Basin does not just contain heavy potassium today. It was already heavy long before those basalts ever formed. The isotope signature was not created on the way up to the surface. It was inherited from below. Something reached deep inside the moon, deep into its interior, and literally cooked it. Numerical simulations of the South Pole Aitken impact suggest it could have pushed mantle temperatures to around 2,800 Kelvin. That is more than hot enough to vaporize potassium. And the moon has no atmosphere to hold vapor in place. Anything that boils simply drifts away into space forever. The most remarkable part is how little needed to escape to leave a mark. Under vacuum conditions, isotope separation is brutally efficient. Modeled as a simple distillation process, the loss of just 2% of the potassium in that entire region would fully explain the signature measured in those 4 tiny fragments. For iron, less than 2%, just 2%. That is all it took to leave a chemical, fingerprint still readable 4.25 billion years later. That is like tearing 2 pages out of a book and having the story of the entire library rewrite itself around it. Hold that thought, because I want you to feel what that actually means. Right now, in a laboratory in Beijing, Scientists are staring at a chemical echo of one of the most violent mornings in the history of the solar system. Before life, before oceans, before Earth even had a solid crust in some places. And they can read it like a book. If this kind of storytelling is something you want more of, from ancient impacts to lost civilizations to hidden discoveries, don't just watch this video, become part of what we do here. A quick like right now, a fresh subscribe if you're new, and a share to that one friend who always sends you space videos. That is what powers this channel. Now let's step even deeper into the story. The paper reporting all of this was published in the Proceedings of the National Academy of Sciences, and it represents something historic. It is the first direct geochemical evidence that an impact of this size can vaporize material deep inside a planetary body. Not just excavate it, not just melt it, but literally boil it. And the consequences of that finding reach far beyond a single basin on a single moon. Volatile elements like potassium and water are part of what makes magma behave the way it does. They lower melting points. They help molten rock rise up through the crust, strip them out of a region of mantle, and that region becomes harder to melt. Rock in that area becomes less willing to erupt, less willing to flow, less willing to form the wide, dark, smooth plains we see when we look up at the moon, which means the very impact that dug the biggest hole on the entire moon may have quietly turned down the volcanic engine of an entire hemisphere. So think about what that really implies. Those dark seas on the near side, the ones every culture on Earth has drawn a face or an animal or a rabbit into for thousands of years. Their absence on the far side may not be some random accident of geography. It may not be luck. It may not be coincidence. It may be scar tissue. Permanent damage left behind by a single catastrophic morning 4.25 billion years ago. An event that reached in and cooked out the ingredients needed for future volcanism, leaving one side of the moon forever quieter than the other. Now, the team behind this research is careful, very careful. They are explicit that this is a proposal, not a settled fact. Their own wording is that the impact contributed at least partially to the observed asymmetry. The measurements are preliminary. They plan to test their conclusion against other volatile elements. They plan to combine the results with numerical modeling to figure out how far across the moon this effect actually reached. But the general shape of the answer is now visible, and it lines up beautifully with something else researchers noticed. These samples suggest the mantle beneath the far side hemisphere appears to hold less water than the mantle beneath the near side. Less water, less potassium, less of everything that helps rock melt and flow. It all points in the same direction. Nearly 2 kilograms of far side material is now sitting in laboratories in Beijing, and most of it has not even been touched yet. Separate research has already started tracing where each individual part of it came from. Scientists have built a catalog of 1,674 major source craters capable of throwing debris onto the Chang'e 6 landing site. Some of those craters reached as deep as 3 kilometers into the surface. Together, those impacts appear to have deposited a layer roughly half a meter thick of foreign debris across the sampling region. The current estimate is that the returned material is about 93% local basalt, about 6% material from the South Pole Aitken Basin itself, the fraction most likely to contain genuine mantle components, and about 0.5% highland material from entirely outside the basin. That 6% is the piece everyone is really chasing. Somewhere in that sealed container, mixed into the dust and the glass beads and the welded fragments, there may be a few grains of the actual inside of the moon. A few tiny pieces of a place no human eye has ever seen and no human hand will ever touch directly. If any of those grains are confirmed to be true mantle material, they will become some of the most valuable objects on the planet. Not because they are rare, but because they are the closest thing we have to a window into the deep interior of another world. The story is not finished either. The orbiter that carried the sample capsule home never came back to Earth after releasing its cargo. It flew on and was captured at a gravitational balance point out beyond our planet, where it remains today, silently orbiting. In September of 2025, the mission team received the World Space Award from the International Astronomical Federation, one of the highest honors in space exploration. Applications to study the samples have opened to Chinese institutions, and the Space Administration has said it welcomes proposals from scientists in other countries as well, and more missions are already coming. Several agencies around the world have their attention locked on the South Pole Aitken Basin, drawn by the permanently shadowed craters near the lunar South Pole and the water ice believed to be frozen inside them. Water ice on the moon would change everything, from future human missions to permanent bases to fuel production far from Earth. If humans ever build a home on the moon, it will likely be in this same region that Chang'e 6 quietly rewrote our understanding of. But step back for one long moment and think about what has actually happened here. For the entire history of our species, we have looked up and seen the same face. Every myth, every legend, every song, every telescope, every observation, every one of the 11 sample returns before this one, all of it aimed at a single hemisphere of a world that turned out to have two completely different sides. We thought we understood the moon. What we actually understood was only the side that faces us, the side that was patient enough to always show us the same view. And when we finally reached around to the other side and grabbed a small handful of dust, what came back was soil too light to be familiar. Glass where there should have been stone, olivine that had almost disappeared entirely, and 4 small stones, no bigger than a fingernail, carrying the chemical memory of a day 4 and a quarter billion years. All go when the deep interior of the moon grew so hot it started to boil. Boiling rock. On the moon. Recorded in a way we can still read today. The dark seas we know so well, the shapes we grew up seeing every clear night, they are not really a feature of the moon at all. They are a feature of the side that got to keep what it started with. The near side simply held on to its volcanic ingredients and used them to paint its face with lava. The far side, hit harder, cooked deeper, lost more, was left barren and pale, a graveyard of what once might have been. 2 sides of the same world, shaped forever by one bad morning long before there was anyone around to feel it. And that is maybe the most humbling part of this entire discovery. A single event, so ancient that our brains can barely process the timescale, ended up shaping how a whole world looks to every human who has ever lived. Every child who ever pointed at the sky. Every sailor who ever navigated by moonlight. Every couple who ever kissed under a full moon. Every scientist who ever tried to explain why the moon looks the way it does. All of it, secretly, quietly, sits in the shadow of a single impact from a time before time really mattered. Chang'e 6 didn't just bring back a small container of dust. It brought back a piece of the truth. It brought back the missing half of a story we have been telling ourselves incomplete for as long as we have existed. And there is something almost poetic about the fact that after all our myths and our legends and our poems about the moon, the real story turned out to be even stranger than any of them. A world with 2 faces, one remembered, one forgotten. And now, finally, one of them speaking to us for the very first time. The next time you step outside and see the moon hanging quietly in the sky, remember this. You're only ever seeing half of the story. The rest of it is being read right now, one microscopic grain at a time in a laboratory on the other side of the world. And whatever we find next may change what we think we know about not just the moon, but about every rocky world in the solar system, including our own. Because if a single impact can rewrite an entire hemisphere, then somewhere in Earth's deep history there may be a similar day we have not yet uncovered. A day that shaped who we are without ever leaving a name behind. So keep looking up. Keep asking questions. And keep watching, because the universe is still full of half-told stories, waiting for someone brave enough, curious enough, and patient enough to bring back the missing pieces. The far side of the moon has finally spoken, and what it said is only the beginning.